This video gives a brief aside on how to define a well-posed predictive control law for an unstable process. Previous videos indicated that there are many problems in doing a GPC algorithm of an unstable process. So although the closed-loop control laws often are stabilizing and appear to give good closed-loop performance, actually the underlying predictions are often far from desirable trajectories, and you could say it's rather fluky or lucky that something reasonable comes out. The mismatch between the optimized trajectories and the actual behavior indicates that in many cases the optimization is ill-posed, and thus the solutions could be seriously flawed or dangerous. This video introduces the simple concepts in the literature for ensuring a well-posed optimization when you have an unstable open-loop system, and it indicates the more well-accepted techniques which will be covered in a later chapter. Open-loop instability then. The main problem with open-loop unstable systems is the coefficients within the prediction matrices are divergent. So if you had a Karima model, you have an H matrix, you have a P matrix and a Q matrix, and if you look at these with an unstable open-loop process, you'll see that as you go down the rows, the coefficients get bigger and bigger and bigger and basically explode exponentially. And therefore, what GPC is trying to do is take a linear mix of divergent responses in order to give a smooth response with a constant steady state. And clearly this is not sensible, and I'll demonstrate this on a graph here. So what you've got is, if you take the prediction with a single control increment, and it could be something like that, and then you say, alright, what about the next sample? Then the next sample, you'd get something like that. And what about the next sample? And you get something like that. And then you could do one more sample. We'll take 4, that should be just about enough. So there's your predictions, and they could correspond basically to the H matrix times delta UK plus 1 down to delta UK plus 3. So I've allowed myself 4 control increments. The impact of the first control increment is this black line, the second control increment is the blue line, the third is the red, and then the black again. Now, what I'm doing is I'm saying I want you to take a linear mix of those predictions, and from that I want you to give me a response that looks like this. And hopefully you can see this is clearly madness, because I've got 4 figures here which are disappearing off to infinity, and I'm saying give me a linear mix of these numbers going off to infinity such that I get this constant value. And you can see it's just not a good way of setting up a problem. So because the step response coefficients are divergent, if you choose a large output horizon, the H matrix could simultaneously contain values from, let's say, 1 up to 10 to the 16 and bigger. And I've chosen 10 to 16 because normally software like MATLAB will take 16 decimal places, but industrial software may not take anything like close to 16 decimal places. So in this instance, the smaller values may end up being rounded to 0, as the software will generally store only a given range of values within a single matrix. So now, this problem will also be made worse when you form products such as H transposed H. And so you're going to get a lot of rounding errors. And the consequence is that the control law parameters could be dominated by rounding errors and not the optimization, and so the optimization you've done may disappear in a mismatch of rounding errors and numerical ill conditioning. And here's an example of that happening. You can see here I've done a simple predictive control law. I've chosen a control horizon of 2, which is nice and small, keep life easy, and I've simply plotted one of the coefficients of nk as I increase the output horizon. And you can see up to a certain point, MATLAB's got good number detail and whatever, it can cope, but once you get beyond a horizon about 80, the ill conditioning comes in, and now you can no longer trust the result. Now this is of course with MATLAB, which allows a lot of decimal places. The problem could have kicked in much earlier if you had a different piece of software which stored fewer decimal places. So the conceptual solution. How do we deal with this fact that we've got all these mismatch of numbers, we've got a silly optimization that we're trying to mix divergent responses to get something that's convergent? So we've got two challenges. Ensure that the predictions we want to mix to make up an ideal prediction at least have shapes close to what we want. And we're going to revisit this concept in a later chapter when we give you a modern predictive control law. And we also want to eliminate divergent signals from HP and Q so that we avoid numerical ill conditioning. So you can see there's two separate points here. One, make sure that all the numbers are in a reasonable range, but this top one is actually the more important one in modern literature. Ensure the predictions that you're mixing are at least close to the shapes that you want, because otherwise you're asking the optimization to do an awfully difficult task. A simple solution is to find a set of future inputs which will cancel the unstable dynamics. Now what that solution does is it deals with this second point here. It gets rid of the divergent signals. So how can we cancel the unstable dynamics within our predictions? And so the prediction class that we're using is now convergent. Now the algebra to do this can be somewhat messy. So what I'm saying to you, you can skip this if you're not bothered, because the more modern solution is going to come in a later chapter. But I'm literally only going to spend a couple of minutes indicating the historical methods for dealing with this issue. First then, you take the original prediction equations. So I'm doing a Karima model here, and there's the prediction equation we derived in the earlier chapter. And then I'm going to express this in the form of Z transforms. So if I do that, you'll find a Z transform for the output prediction can be written as B of Z times Z transform for the future control increments plus some P of Z over capital A of Z. And the key thing is this P of Z is easy to define. You'll see it's 1 Z inverse all the way up to Z to the minus n times this vector here, which just depends on the past inputs and the past outputs. So that's straightforward to define. Now, next, factorize A of Z into its unstable and stable poles. So I'm going to write A of Z as A plus, that has all the unstable poles, times A minus, that has all the stable poles. Now the output predictions will be convergent if and only if the poles are entirely stable. So if you write down the prediction equation like this, and you notice, but it's got an A plus in it, if I want the future predictions to be stable, then the numerator has to include an A plus. So what I'm going to do is say the numerator must be written as A plus times phi. And I don't know what phi is yet, but we'll worry about that in a minute. And once I've done that, I can see that A plus and that A plus cancel, and my predictions are now given by phi over A minus. And conceptually, that's all that people proposed in the early literature. Next question then is, how do I find the implied restriction on the future control increments, because it's them that I actually have to choose? Well, what we've done is we've said that our numerator has to satisfy this identity. B of Z times delta U future of Z plus P of Z, and this obviously changes every time, equals A plus of Z times phi, where this phi is some polynomial. And in essence, all we have to do is solve this identity. Now, I'm not going to go through the solution. It is in the historical literature, and it's relatively straightforward to do. You get a simple linear expression, and you can show that if you choose the future control increments to be some function of P, and that's just simple matrix algebra that gives you the dependence on P, so that's easy to find, and then you'll get an A plus, and then this phi is actually totally free. I should put that down. This becomes your degrees of freedom. So you now can choose the phi however you like. So if you do that, if you choose the future control increments to follow this equation for an appropriate f of p, and your phi, or psi, sorry, is totally free, it's the bit you can choose, and now you can substitute that into your predictions, and you have an optimization based upon this psi variable, and all your predictions are convergent. Now, I've not really gone into any detail there because more modern methods are perhaps a better way to follow. The other thing to note is there is a conceptually equivalent parameterization approach for state space models, which is in the literature, and again, that's why I'm not going to dwell on it here. So the conclusions. if a system is open loop unstable, it's important to parameterize the predictions in such a way that they're convergent before you put them into the performance index. And this helps ensure both a well-posed optimization and also avoids the danger of numerical ill conditioning. Now, algebra and pole cancellations are straightforward, as we've indicated here. However, and this is the key thing, better alternatives using closed-loop prediction are more favoured now in the literature, and that's why I've deliberately kept this video very brief, because there's no point overplaying detail which is not likely to be used, and I would recommend you follow the closed-loop prediction routes, which are now more favoured, and I will discuss later.